Hello and welcome to episode number 10 of CS350 Online. I'm your host Leslie, and in today's episode we're going to continue our discussion of processes, but this time we're actually going to take a look at processes from the perspective of system calls and how they all work inside of the kernel. But of course, let's start with our OS of the day. Now, today's OS is one that I don't actually anticipate many, if any one of you have heard of, despite the fact that it's actually been around for quite some time and it still technically exists. But it's called PIC. And PIC was released commercially in 1973, but was available by other means from about 1965 on. And this operating system was named for and created by a gentleman by the name of Dick Pick, and he ran TRW Inc. And what's really interesting about the PIC operating system is the fact that it was Unix's major competition in the 1980s. So it was really surprising that you can have an operating system compete with Unix, and most people have never heard of it. Now, PIC is a very different operating system from everything we've seen so far. Yes, it does offer all of the things that we would expect an operating system in the 1970s to offer. Things like multi-user support, time sharing, virtual memory, anything like that. But how PIC is implemented is very different. So it's actually based on a database. So they have a hash-based database system that's going to give you quick retrieval for files and records, and just general management of the system is going to be through a querying language. Now, they also offered a procedural language and a compiled basic language, and it had all those major OS things, but it's just phrased around a database app instead of, a traditional OS. Now, if you actually go on YouTube, and maybe I'll post a few links to this, PIC was a really big company. And this is really surprising because most people have never even heard of it. But there are these, I think they're annual ComDev conferences that usually happen in Vegas, and companies would spend a lot of money marketing. And I'll post some of the very amusing ComDev live shows for PIC. They are entertaining. But it'll give you a sense of how big and how popular PIC was 30, 40 years ago. Now, PIC is not an operating system that was really meant for your everyday user. It isn't something you would use in your household. This is something that's meant to be used by a company because households don't need databases. So technically I might have a database to keep track of all the things that are on my network because even my light bulbs are attached to my network. Don't ask. But the average household user doesn't need that. But if you look at a company, there's so many aspects of a company's daily life which would revolve around large amounts of data that would need a database for, that a database-based operating system, when that's optimized for that kind of behavior, makes a lot of sense. So this was big with companies and businesses. And it isn't actually an operating system anymore. So it used to be its own operating system. However, it is around as a database software that you can actually install on top of Windows. And I think it's been in that state since the 90s, but don't quote me on that. But it's kind of neat still. All right. So, still in use today, which is kind of fun. And I will post some of their interesting videos to Piazza so you can have a good laugh. And if you really want to have a good laugh, search out on your own for like old 1980s and 90s ComDev videos. They are quite amusing, let's just say. People don't get as excited about software and operating systems today as they did, 20 or 30 or 40 years ago. 30 years ago, people got so excited they would spend like $1 million trying to just entertain people at the release party. They'd bring in bands. They'd make their own rap songs. Like, you'll understand when I post the video. It's good fun. All right. So that's PIC. So what were we talking about last day? So last day we were actually talking about processes. And in particular, we were talking about these process management calls. So remember that the process management calls are things that we are doing to manipulate a process. So that's things like creating processes, changing what program a process is running, terminating them, providing synchronization between them, and getting any kind of attributes of those processes. And we saw how to get what those attributes were because we looked at top and we looked at PS, and we saw how we could get things like their PID. We can get how much processor they're using, how much memory they're using, how many threads they have, the state they're in. And you can actually go deeper and get their user ID. You can modify their weight of the process, which will give the process's threads either more time or less time on the CPU. But these are all process management calls. These are actually all high-level things provided to the user to work with and manipulate the processes. But their implementation doesn't exist at a user level, because you can imagine that if you want to start having processes synchronize with each other, that's going to probably involve the kernel in some way. And if we want to keep track of the different attributes of a process, we're probably going to need to involve the kernel in some way. So today we're going to take a deeper look at some of these process management calls from the kernel's perspective. So this is slide 9 for those of you who are following along. Make it nice and big here. All right. So all of these different process management calls are actually the user side of what we call system calls. Now, what is a system call? Well, there's a lot of things that we don't want a user program to be able to do. For example, I don't want my user program written by some random individual on the internet, somewhere on the other side of the world. I don't want that program that I can't trust to be able to just start writing directly to the files on my disk. Because if I let them access directly the data on the disk, then who's to stop them from getting at sensitive information like my passwords? Or who's to stop them from getting at sensitive information like the data structures contained in the kernel? It would be very bad. So we actually want to isolate the user from the kernel because we really don't want users or user programs to be able to directly access or communicate with the kernel or any of the underlying hardware. We want to abstract all of the functionality of file writing and just general file management and working with processes. We want to have that all abstracted away such that the user is not actually participating in the low-level implementation. They don't know anything about it. And that's actually what a system call is. So a system call is actually the interface that exists between the user process and the kernel. Because what we're going to do when we save a file is we are going to use a system call to ask the kernel to do it for us. That way, the kernel can safely abstract the implementation of the device drivers and the file systems for that disk. And we, the user program, don't have to know anything about it. So, I've already talked about the security reasons why we don't necessarily want user programs to be able to access the underlying hardware. And likewise, we don't really want user programs to be able to access the kernel's data structures. That would be really bad, actually. But another big reason is if we don't have an API, this abstraction between the user and the kernel, then anytime you do an update, whether you are on Linux, whether you are on Solaris, whether you're on Windows or Mac OS or Android, it doesn't matter. I don't want kernel updates to cause my user programs to no longer be able to function. So we need to abstract all of the actual core functionality and devices away from the user program, and we provide the user program with access to those things by system calls. So the user doesn't actually know anything about the implementation of those things. That's hidden away tightly inside the kernel, but they have an API they can use to get that functionality. So aside from our process management calls, which are things like fork and execv and wait PID and get PID. And I've already mentioned that file access, so opening, closing, removing, reading, writing, checking the size of files, all of that is information that only the kernel knows and only the kernel should know. And should know how to access. So we're going to have to make a request to the kernel to get that information for us. We've even abstracted how files are implemented away from the user program, so we don't need to keep track of what kind of file system or what kind of disk that's stored on. All we need to know is, are you reading or writing? What are you reading or writing? And where is that file located? Then we've got things for managing the file system itself, which is things like the directory structure. And then we've got things like inter-process communication. So processes are generally considered to be completely isolated from each other. However, there are situations where you actually would want processes to be able to communicate with each other. And we will talk about those a little bit later today. But IPC, or inter-process communication, all of the calls associated with that are also system calls. Then we've got things for managing virtual memory, like SBRK. And that's for doing things like increasing the size of your heap or increasing the size of the stack. So there are actually system calls that can help you change the size of the different segments in your address space. Of course, you don't want to be able to do that directly, hence a system call. And then you've got things that are related to the system itself, like the ability to reboot. You don't want the user program to know the exact stages to perform a kernel reboot. You just want the user program to say, hey, kernel, I need you to reboot. And the kernel can handle secretly whatever it needs to do for that reboot. Asking for the time, changing the voltage of your CPU, those are all kind of system management level things that we don't want user processes to know the gory implementation details of, for both security reasons but also for good data abstraction reasons. So we're going to hide them behind this system call API. And you've probably heard me use this example of changing the voltage of your CPU several times, and you're probably thinking, what the hell does that even mean? So the backstory there is that my first laptop I bought, I think, in the beginning of 2003, and it was a Dell Inspiron 5150, and it was the first time Dell had ever put a desktop CPU into a laptop. It's a Pentium 4, and so a very powerful machine at the time. But what they neglected to do is put a proper cooling system in for a desktop CPU. And so this machine had a habit of overheating. Now, one of the ways that you can mitigate the overheating issue is in the system settings for Microsoft Windows, you can actually throttle the CPU down. And the way that you actually do that is by reducing the CPU's voltage. So you could set it to be like 70% of the voltage that it should have, and that would actually, yes, your computer's going to operate slower, but because you've decreased the voltage, you're actually decreasing the amount of heat that gets generated. That is a system call, and I don't really think Windows lets you do it that way anymore, because that's very confusing, but it was a fun thing you used to be able to do. That computer, by the way, I'm sure you might have seen some memes on Reddit, me talking about a computer that went down in flames. That is the computer that went down in flames many years later. I actually had the BIOS, for some reason, catch on fire and fire shoot up from the keyboard. And if you need visual proof, I can post. I don't have photos of the fire, but I do have photos of me having to reinstall the computer while it sat in the fridge. Don't do that. All right. So let's talk more about the relationship then between the user application, the system calls, and the kernel. We're not going to worry about the hardware right now because we know we don't want the user program interacting with hardware directly because many reasons. So So we have our user application here. In the user application, that's, Red Alert 2, that's Unreal Tournament, that's Warcraft 3, that's any of your actual user programs, Chrome and so on and so forth. Then we have the system call library. The system call library is that API that is provided to the user programs so that they can do things like save and write files and interact with other processes and so on and so forth. Now, what you'll notice about this diagram is we've actually divided it into two parts. Everything above this dashed line is what we call unprivileged code, and everything below the dashed line is what we call privileged code. Now, sometimes we call this user privilege, and sometimes we call this kernel privilege. Now, what this distinction is not just some hand-wavy, written-on-paper distinction. This is actually a distinction that's made in the CPU itself. Your CPU has different modes, and what these modes are doing is restricting what kinds of instructions and memory addresses you can access depending on the mode you are in. We want to prevent user programs from accessing the kernel's memory, and we want user programs to not be able to access things like directly changing the voltage of the CPU or directly calling instructions that would cause the computer to reboot. And so in order to prevent the user program from using such assembly instructions and accessing private memory addresses, the CPU actually has rings or levels of privilege. And for now, we're only going to talk about two of them, and that is privileged and unprivileged. Because unless you're really talking about virtualization and VMs, we don't typically see more levels used. Okay, maybe more recently we do, but in the past you don't. So this is actually a mode on your CPU that says, oh, excuse me. This is actually a mode on your CPU. And if your CPU is in unprivileged mode, then there are certain assembly instructions that simply can't be executed. And there are certain memory addresses that can't be accessed. Whereas if you are in privileged mode, then you can technically execute and access everything. So this isn't just some theoretical line. And then the idea here is the application wants to write to a file, so it calls the system call libraries API. That API function is going to somehow, wavy hands here for a minute, access the kernel's implementation of opening a file. The kernel will actually do the opening of the file. It will produce a return value, which it passes back to the system call library, and the system call library will format that result and pass it back to the application. Just how does this division work, though, and how does it affect things? So this is a way of isolating user programs from the kernel. And as I said, it's going to prevent the user program from accessing certain instructions and regions of memory. And we're also using it in a way to prevent the user program from actually being able to call a kernel function directly or access any kernel's data structures. So this actually leaves us with an interesting question. Your user program and the system call library, which live in unprivileged land, are not allowed in any way, shape, or form to directly call a function inside the kernel. They're also not allowed to access any of the kernel's data structures. We've isolated user land from privileged land. So if you've made this distinction, if you've done this isolation, how then do you actually open a file if the system calls version of open can't actually call the kernel's open? Interesting thing to think about. Now, an interesting little story on this topic of kernel privilege and how kernel privilege is supposed to prevent us from accessing certain regions of memory and certain instructions when we're in an unprivileged state. Many of you may have heard of the Meltdown and Spectre vulnerabilities, which were found in Intel CPUs 2 or 3 years ago. And what those vulnerabilities were was due to the fact that your CPU reorganizes instructions and tries to it looks ahead for loads. And when it can see that, hey, I'm going to need to load a bunch of things, and I could technically load them now and cache them so that when the instructions that use them actually execute, they're here and ready. The problem is that the instruction reordering ended up happening such that privileged loads for things that are in privileged memory, ended up happening silently when unprivileged code was running and the CPU was in an unprivileged state. And so you end up getting privileged values being stored in the cache, which is in an unprivileged state. And because the check to see if we should have been allowed to perform that operation may not happen for several instructions down the pipeline yet, you can do a cache attack where you can try to inject yourself into the cache and steal those values that have been pre-cached but were technically privileged data. So you're effectively, Meltdown and Spectre were letting us bypass this privilege and steal secrets from the kernel. I'll actually post the papers for these, if I remember, to Piazza. Now, many of you probably, I'm sure, don't know much about security, but I'm not a security person either. And I found these papers to be really approachable for someone who doesn't really have a background in that area. So if you're interested, and I forget, please do remind me and I will post those to Piazza. They're quite interesting to read. Okay. This still brings us to the question then, if the user program isn't actually permitted to, and the system call library also living in an unprivileged state, isn't actually permitted to do any of these direct accesses to kernel data and kernel function calls, then how do they actually get the kernel to do anything? Well, actually, you've had the answer the whole time. The only two things that can cause kernel code to run are interrupts and exceptions, aside from boot, of course. So we already know about interrupts. We know that when an interrupt is fired, interrupts being things that are generated by devices, we know that interrupts are going to cause the CPU to stop executing whatever thread it was doing at that time, and it's going to immediately start executing the code for the trap frame. So it's going to stop executing the thread, and then it's going to jump to one of these addresses for an interrupt handler that it stores in its trap table. And the first thing that interrupt handler is going to do is save the trap frame, so save the contents of every register. And then it's going to call something that's going to cause it to figure out what kind of interrupt was just fired and what is the actual interrupt handler that I need to call in order to handle the interrupt that has happened. So in the case of something like a clock, we are going to recognize an interrupt is fired, we will save our trap frame, and after we save our trap frame, then we'll be like, oh, it's the clock. Okay, I'll call the timer interrupt handler. Okay. So when that interrupt gets fired, there's something else that's going to happen almost simultaneously. And it really comes down to architecture as to how this is implemented. But what's going to happen typically is when the interrupt gets fired, because we are going from a user state and we want to start executing kernel code, we need to switch our privilege. And so the CPU usually flips itself into a privileged mode when it receives that interrupt, and it jumps to that instruction in the interrupt handler, which is a part of the kernel. So we are going to flip our execution privilege to privileged mode when we receive the interrupt. And that is actually quite safe, by the way, because at the point you receive the interrupt, we actually cease executing our user thread. Now, what's an exception then? So an interrupt is your computer responding to events from devices like key presses, this microphone receiving an audio signal, which I know is continuous, pushing on the mouse. I've got a little ring light there, pushing the remote for that. Those are hardware interrupts. An exception is something different. So an exception is going to be caused by the execution of the program itself. So if you have an arithmetic overflow, if you do a division by 0, that's actually going to cause a software exception. That's an instruction that the CPU cannot execute correctly. And so the CPU needs the kernel to handle it for it, because the CPU is like, I've divided by 0, or I'm trying to divide by 0. I don't know what to do. I'm so confused. Kernel, help me. And so when the CPU receives that exception, or throws that exception, because it doesn't receive it, it throws it, we're going to also flip it into kernel privilege. We will also cease executing whatever thread we were executing, and we're going to execute an exception handler whose address is also stored in the trap table. And then what's going to happen is in the exception handler, we're also going to figure out, okay, well, what exception did you throw? Was it an arithmetic overflow, or did we have a page fault? Was the user program trying to execute an instruction that they're not allowed to execute? And then we will call the handler that is appropriate for them. So these are the two ways that we can go from user privilege into our privileged kernel land: an interrupt and an exception. And it's through exceptions that we are going to build the ability to have a user program write to a file. So a little bit of architecture-specific details here. First off, on our Mips CPU, it doesn't differentiate between interrupts and exceptions. So it actually considers everything to be an exception. So an interrupt, that's an exception. If we divide by 0, that's an exception. If you have an arithmetic overflow, that's an exception. You tried to write to null, that's an exception. Tried to write to an invalid address, that's an exception. Everything in Mips is considered an exception, which makes it kind of convenient because what you're going to end up with is your trap table only needs to contain a singular address of the one and only exception handler. So in Mips, because everything is exceptions, we actually have a number of different exception types. So EXIRQ, that is our true interrupt. Now, you might be wondering, why are we calling it IRQ? I don't know. I don't know why this is the abbreviation for interrupt. I just know that it always has been. And I remember seeing this back in playing with device drivers for Windows 3.1. It's been IRQs for a very, very long time. So anytime you see IRQ, that means interrupt. Then we have the rest of these as being traditional exceptions. So we have EXOVF, exception number 12, that's an arithmetic overflow. EXRI, that's an illegal instruction. We've got breakpoint, that's actually more for the debugger. Then we've got these TLB miss on load and TLB miss on store. And I've noticed a number of you on Piazza are already getting these. And I will make sure that I post a little guide as to what exactly those mean. But essentially, this is how segmentation faults get presented to you, is through TLB miss and TLB miss on store. So this is, you are trying to access an address on a read that you're not allowed to access or doesn't exist. And you're not allowed to. And this is, you're trying to write to an address you're not allowed to. And then you've got things that address error on load, and that means stuff like this isn't even an address. So all of these things are all more of your software exceptions, with the exception of the first one, which is going to be your hardware. Now, the one that we are going to use in order to enable us to do system calls is EXSYS number 8. This is the system call exception. What we are going to do is whenever we want to have our computer write to a file, we're going to raise an exception to flip us from user mode into kernel mode so that we can execute the kernel's version of opening a file or saving a file or forking a process or getting our PID or what have you. So instead of doing this through the slides here, what I'd actually like to do is actually just draw it out for you and actually walk you through some code. So we're going to kind of deviate from the slides a little bit because nobody wants to read slides anyways, right? So let's open up something here. Of course, OneNote likes to open on the other screen and then promptly disappear. I know you can't see my setup in full here, but I have a 38-inch widescreen monitor sitting beside me, which is not my master monitor. It's supposed to be the slave monitor, but it, for some reason, OneNote likes to open on it. That's not how it's supposed to work. All right, new page. So, let's get some paper. Ooh, grid. Grid's fun, but I don't want a grid. There we go. Okay. So let's suppose that I have some kind of user program. And it wants to, let's, for the sake of discussion, we want to call fork. So I want to create a new process. So we want to create a new process. Okay. We want to call fork. So what is going to happen inside of fork is I need to raise the system call exception. And how I do that is with a call to syscall. So this is our instruction. It's an assembly instruction. To do this, raise the exception. Okay. But is that enough? Is that the only thing that I need to do? Well, think about this. How many different kinds of system calls are out there? There's forking, wait PID, exec v, get PID, exit, open, close, read, write, printf, sbreak, reboot, time. I could go on and on. There could be potentially thousands of different kinds of system calls. Are you telling me that there is a separate assembly instruction for each of those system calls? Because that doesn't actually make any sense. Because keep in mind that when somebody creates an architecture like a physical CPU, they don't know what OS you're going to run on it. So they're not going to, and they don't know what OS you're going to run in the future. They don't know how Windows is going to change in the future. So you can't have the architecture actually provide a separate assembly instruction for every possible system call that could be made. So we are only going to have one instruction to actually raise the system call exception. But then we need some way of communicating to the kernel which assembly or which of those system calls you actually wanted. So into register v0, and I may have the syntax for this Mips wrong, but it'll be fine. Actually, I know I have it wrong. So what I'm going to do is into register v0. Oh yeah, that's fun. Thanks for crashing OneNote. Into register v0, I'm going to store what's known as the system call code. Now, the system call code is a unique identifying integer that's going to be decided upon by the kernel and shared with the user program to indicate if you use code 0, that means fork. Let me show you what I mean. So we're going to go over here. I don't think you want to see my curve code. And let's get out of our process structure. So I'm going to go So we are in kern include, and if you look inside of kern include, there's another directory called kern. This is something called the application binary interface. This is information that the kernel does share with the user program so that system calls can be made, so that errors can be properly passed back and forth, and so on and so forth. None of the information inside of the kernel's application binary interface, or ABI, is secret. There's nothing secret in here. You're not giving anybody access to anything that's going to harm anything. So if you go into syscall.h, what you will see here is the system call codes for each and every possible system call that this operating system has considered. So for us, fork is 0, execv is 2, exit is 3, wait PID is 4, get PID is 5. There you go. And there are system call codes in here for pretty much everything. So here's ones for virtual memory, things like increasing the size of stacks and heaps. Then we've got stuff related to user IDs and security. We've got signals, so things like killing a process and so on, suspending things. We've got things for handling files, reading and writing. We've got things for path names. We've got things for directories. We've got symbolic links. We've got mounting and unmounting file systems. I've got changing the ownership of things. I've got changing the stats of a file system. I've got stuff for sockets and networking, so getting a socket, binding a socket, connecting to a socket, listening to a socket. All of those things are system calls. Getting the time, rebooting. So in syscall.h, which is found in kern include kern, this is the part of the kernel's ABI, what it is providing to the user so that we can indicate to the kernel when we raise that system call exception, which system call do you actually want? All right. Now, is that enough information? And the answer is no, it's not enough information. Some of our system calls, for example, execv, have arguments. What about the arguments? Well, we need some way of passing those arguments from the user down into the kernel. So how we are going to do that is via registers A0 through A3. So we're going to load our arguments into A00 to A03. I don't actually think those are prepended with zeros, but it doesn't matter. You get the point. And I see a comment on Twitch. Ooh, I saw that somewhere commented out. Seems like we need to implement it. No. So this operating system has actually got a lot of features which are not implemented and aren't even close to being implemented. We are not expecting that you're going to implement anything with respect to sockets or file systems or anything like that. We're going to stick to just, system calls for processes. And I know that might mean you're a little disappointed, but do you honestly want to do more work? There's no bonus marks in the course, right? So don't do more work than you have to. All right. For the record, when I took this course, which I think was I don't remember. It was like 15 years ago. We did have a file systems assignment, but we don't have one anymore because we don't cover file systems until the last few weeks of the course, and that doesn't really seem fair to have an assignment due that you just learn the material for when it takes a lot of coding work. And I see some of you are not disappointed that you don't have to do extra work. You guys have enough work to do as it is. You don't need us piling on even more work. All right. So in order to do a system call to raise that exception, we have to do 3 things in the system call library, which is a part of user space. We have to load the arguments for the system call into registers A0 through A3. And if you need more than 4 arguments, then you should be putting the extra arguments on the stack or the heap and then loading the addresses into the registers. And then you're going to put the system call code into register V0, and then you use the syscall instruction to actually raise the exception. That's how we actually make the call. Now, how do you know what arguments need to go into what registers? That's actually a part of the kernel's ABI. It will actually tell you this needs to go in this register and this needs to go in this register and so on and so forth. So that is information which is not secret and is shared with the user program. Okay. Let's go back to full screen. So you've seen that, and if you didn't hear me say where the address of the system call codes are, it's actually written here in the slides for you. And again, if you can't read my horrible handwriting on the little tablet there, the names of the registers are also included here. Okay, so there they are there. Now, the thing we haven't talked about is return values. So let's go back over here, and let's talk about return values. So fork, for example, returns a value. And it could also return an error code because maybe the fork fails. Now, why would fork fail? Well, in OS 161 as it's implemented right now, fork is going to fail for a number of reasons, including running out of memory. So let's look at all the different things fork could return. Fork needs to return 0 if the process is the child. Fork is going to return a positive integer, greater than 0, that is, if the process is the parent. And fork will return a value less than 0 if we have some kind of error. Okay. So you might be thinking, well, I could have, let's use register V0 for the return, and let's just store the integer value into that. Sure. But what if a negative, and if it's negative, then, that's an error code, and if it's positive, it didn't error out. It works sometimes, but that doesn't always work. And it doesn't always work because sometimes a negative value is a valid response. So a single register isn't actually sufficient for doing returns from system calls because we can't necessarily differentiate between this is an error code and this is an actual output of the system, the return value of the system call. So we're going to use 2 registers for return. So we have V0 and we have A3. And I always forget which one is which because I always forget which one is which. Okay, there we go. It's too early in the morning for me to remember things. So into register A3, we're going to put one of 2 values. Success, which is 0, or fail, which is 1. And depending on what you put into register A3, that's going to determine what is actually the return value for the function. So into V0, if success, I put the actual return value. And if we fail, then V0 contains the error code. So we are not returning one thing from a system call, we return through 2 registers. A3 is going to indicate success or failure, and then V0 is either going to be the return value or the error code. And the system call library, which is part of user privilege land, is going to be like, all right, I see that A3 contains success, therefore V0 contains my return value. Or, oh shit, A3 has fail, therefore I've got an error code I've got to deal with in V0. And again, the different error codes that can be returned are going to be a part of the kernel's ABI. And I'd actually like to show you some of the error codes here. So let's go back into the ABI and let's get out of syscall.h. And you can see we've got error message and error no. So I'm going to open up error no first. apologize if you hear any silly giggles and stuff. As I've mentioned before, my 6-year-old is attending virtual school. So she's actually doing synchronous virtual school in my basement with my 2-year-old beside her. And sometimes it gets very silly. All right. So here are some of the error codes that the kernel might return. So we've got eno-sys, which means there's no such system call. Then we've got things like out of memory, eno-mem. And let's suppose that there are too many processes in the system. Well, then there might be enproc. Or maybe there's no such directory. Then we could say eno-ent. Or maybe the device is broken. Then we've got these error codes related to the device. So my point I'm trying to make is, as part of the kernel's ABI, not only do we have these files that indicate what system calls are available to us, we also have a list of error codes. And if you open error message, it should be the message that you display. You want to make sure that the kernel's messaging for what an error should be displayed as matches up with how that is presented to the user program. Because that's going to make sure that whenever we're doing some kind of debugging for a kernel-based thing, like a system call, we actually can map the error the user sees to the error the kernel actually was supposed to give. I mean, it would be like getting a blue screen of death. Imagine this. You get a blue screen of death because your NVIDIA driver died. I mean, I've gotten that one like so many times, it's not even funny. And let's suppose that your blue screen of death, instead of actually giving you like a meaningful error code and a meaningful message, maybe the user side implementation of a blue screen starts like dancing and trains start going across the screen and says, haha, your driver died. That's not helpful. So we've got to make sure that error messages that are stemming from something happening in the kernel, they've got to be consistent. So we provide this ABI here. So that's a fun one. All right. So let's go back here. So now you can actually see a little bit more how we're actually going to make this work. All right, so what happens, going into a little greater detail, and we're going to go into an even finer grain detail here in a minute by actually looking at the code for this. But the application calls fork. Fork is a high-level system call library function. That's printf. You know how you call in stdio? You're getting access to the system call libraries there. So you make a call to, you include that, and then you make a call to printf. And what's going to happen in the user side implementation of printf is it's going to load the arguments into registers A0 through A3. It's going to look up the system call code for printf, and it's going to load that into register V0, and then it's going to raise the system call exception. At the point of the system call exception, the kernel is going to flip into privileged mode. It's going to save the trap frame, and then it's going to call the exception handler to figure out what kind of exception is it. It realizes it's a system call, and then it realizes, oh, it's printf, because it looks in register V0. And then it's going to say, okay, I need to call my implementation of printf. The kernel will do the work of printf, and then it will load into V0 and A3 the return values. We will flip back to unprivileged mode where the system call library grabs the return values from those two registers and then passes them, formats them back up to the application. So much work is being done here. The question that I have for you is, are system calls expensive? The answer is they're very expensive. Think of it this way. Let's suppose you want to print the numbers from 1 to 1,000,000 onto the screen. This is actually one of the very first computer programs I ever wrote. I wrote it for Commodore 64 when I was like 12 or 13, written in BASIC. And we wanted to know, how long does it take a Commodore 64 to print the numbers from 1 to 1,000,000? So we didn't use a loop. We had to use a goto because it was basic. But we had effectively a loop that called print 1,000,000 times. Okay. So, sorry, I'm hearing my I have a Muay Thai gym in my basement. And I can hear the heavy bags moving around. And I was like, what is that weird sound? And it's like, oh, apparently they're doing Muay Thai down there. Somehow I don't think that's part of grade 1. Anyways, so you have 1 million calls to print. If each call to print is a system call, that's a lot of work. You got to load the parameters into those registers. You've got to load the system call into that other register. Then you raise the exception. The CPU is going to flip into from unprivileged to privileged mode. Then we've got to save the trap frame. Then we've got to call the exception handler. The exception handler has to figure out if it's a system call. Oh, it's a system call. Now I got to figure out which one it is. I call print. I do the work. I make the return values. I restore the trap frame. I'm running out of breath. And now I'm going to do this 1 million times? This doesn't make sense. So if you have to print the numbers from 1 to 1 million, don't do it in a loop. And have that 1 million calls to printf, because that's 1 million system calls, and that's going to be really slow. What you want to do is actually take everything you're going to print, shove it into a giant string, and then make 1 call to printf. Much, much faster, because there's fewer system calls. And by the way, if you're wondering how long did it take the Commodore 64 to print the numbers from 1 to 1 million, the answer is 12 and a half hours. Yeah, computers when I was a kid. Oh, I love Commodore 64s. They were so much fun. I actually tried to rerun that same piece of code in like a basic emulator. Well, I couldn't get a basic emulator working on my Mac, for number one, because I didn't have enough time to actually sit there and fiddle with it. But the same piece of code written in like C++, it was like not even a minute. It was so fast. It's hilarious. Oh well. Commodore 64s were still fun. Okay. Now, before we actually look at the code that does this, what I'd like to talk about is one more piece that we're missing here. And the piece that we're missing here is actually, what about the stacks? So as you know, every time a function executes, it's going to make liberal use of the stack for loading and saving, the caller and callee save registers, but also, for just saving like its own local variables, they get put on the stack. So we have this stack frame. So if every thread has 1 stack, and we don't change threads during system calls, you don't go from executing the user thread to execute, a kernel thread. We're still technically executing the same thread here. So are we really going to put the kernel stack frames onto the same stack as where we have all the user stack frames? Because if we're trying to keep the kernel and the user program isolated from each other, that actually seems like a really bad idea. And it's a bad idea for a number of different reasons. So number one, there's the obvious security breach or potential for a security breach. And the potential is that we are putting sensitive kernel data onto a user stack or a stack that the user could easily access. There's another problem too. We like to think of, due to CS136, that stacks can just grow and grow and grow, but memory is finite. And we actually set an initial maximum size for our stacks. So in OS 161, the maximum stack size is actually 48 kilobytes. And you might be like, oh my God, that's so tiny. But it's like, the programs you are running are effectively hello world with threads. 48 kilobytes is more than enough space. But even something like the Linux kernel, even Mac OS, even Windows actually have a maximum initial stack size. And you might be thinking, oh, it's got to be like 256 megs, right? Right? No, it's not. It's like 1 meg. 1 or 2 megs. That's it. Now you can actually set up the program to start with an initially larger stack, but by default, the initial stack size is only a meg or 2. It's really small. Want some proof? Okay, here's a program that you can write to have a little bit of fun. So what you want to do is to see how big your stack is, or to show you that you can actually overflow a stack in a user program on something like a new Linux operating system or Mac OS or Windows. What I want you to do is I want you to create something really big on the stack. Now that's actually really hard, because if you just try to create an array of integers, that's not enough. So what you have to do is you have to make like a struct with a large array inside of the struct, and then make an array on the stack of those structs. Calculate how big, like you could parameterize it a little bit if you wanted, calculate how big it's actually going to be, and then run your program and see how much data can you actually fit onto the stack before your program crashes with the Stack Overflow. So that's a little program you can have fun with on your own computer to test just how big your stack really is. And what you're going to find out is it's not that big. It's really not that big. Of course, there are system calls that you can use to actually change that, but by default, no. Okay, this actually brings me to an interesting discussion. Let's suppose that the user program brings the stack to the last final 4 bytes before it would overflow, but it would never actually overflow. Because then what's going to happen is if you have a system call and the kernel is going to share your stack with you, then the kernel's own stack frames would cause your user stack to overflow. And the user program would crash, but the user program did nothing wrong. So for both security reasons and for, not wanting the kernel to overflow the user program and cause it to crash, we keep user and kernel stacks separate. And in OS 161 in our Mips system, and in many OSs, every thread doesn't just have one stack, they have 2. There's the user stack where only user code goes, and then there is the kernel stack where all trap frames, switch frames, and stack frames corresponding to kernel functions are going to live. So we'll separate them. And that means that when an exception or interrupt is raised, not only do we switch from unprivileged to privileged mode, we're also going to have to flip from using the user stack to the kernel stack. And then when we go back, we have to flip back. All right. So I don't want to go through these next couple slides here, which are walking you through the code. It's just 2 slides, 22 and 23. I actually want to open up the code and show you again where this all goes down. So let's go back over here. So we're in the kern directory, so the top level kern, and we're going to go into Arch. And then we're going to go into Mips, and then we're going to go into low core. And you're going to see some files that end in .s. Anything that ends in a .s, that's an assembly file. So we're actually going to go into exception mips1.s. And I'm going to go down to, I'm looking for a label. There it is. On 104, you will see common exception. Common exception is the common exception handler. This line here, this is the address of this instruction, that is going to be what is stored in the trap table for our CPU, such that when an exception or an interrupt is raised, this is the address of the code we are going to start executing. Now, what this code does is it checks to see if we were in user mode when the exception was raised. And it's going to check a special register for that, K0. And if we were in user mode, then we need to find the kernel stack and switch to the kernel stack. So that's what you're seeing here. So if we were in user mode at the point of the exception, then we are going to find the kernel stack and switch to it. If we were in kernel mode, however, because exceptions and interrupts can still happen while the kernel is running, we don't need to switch our stacks because we are already using a kernel stack. We are also going to disable interrupts. While I am handling and just figuring out what the hell just happened, I don't want to be interrupted again. So interrupts are off. We are in privileged mode, and we have our privileged kernel stack for this thread. Okay. Now what we're going to do is we're going to make some space on the stack to store our trap frame. And then what we're going to do is save the trap frame. So there's us saving some very OS specific things like the K registers and the GP, global pointer. And then we save our S's, our T's, our A's, our V's, and everything else, and our return address. So this is us saving the trap frame. And then we load from the kernel or the CPU all of the special registers, and we're going to save them as well. After we've loaded all of the information and we save the information about the context of the exception, what we're going to do is on line 260, our trap frame is saved on the stack. On the kernel stack, we are going to jump and link a function called Mips trap. Now, Mips trap is not actually in this file. Mips trap is in trap.c. Here it is. So Mips trap takes a pointer to the trap frame, and that is the trap frame that we just stored on the stack, because a lot of the information we need to handle the exception is actually stored in that trap frame. In particular, if this is a system call, then registers V0 and A0 through A3 contain information we need to actually execute our system call. Interrupts at this point are still off because all we have done is saved our trap frame. Now we need to figure out what was the exception. So we're going to grab the exception code and we're going to check first, is it an interrupt? If it's an interrupt, we're going to call the interrupt handler, which is called main bus interrupt. You can think of main bus interrupt as a dispatcher. So main bus interrupt is going to recognize the fact that hardware has thrown an interrupt, and it's going to then figure out, okay, what device? And then it's going to call the appropriate handler for that appropriate device. Interrupts will remain off for now if it is an interrupt. And we'll let main bus interrupt and the appropriate interrupt handlers actually handle turning that back on again. If, however, this is not an interrupt, that is, it's a memory exception, a system call, or any other kind of software-based exception, we're going to turn interrupts back on again. The reason why interrupts are disabled for handling of an interrupt exception is because interrupts are breaking up the natural flow of the code that was running. They are happening without the knowledge of the thread that was running, and we want to make sure that when we are interrupting code that didn't do anything wrong, that interruption is as short as possible. So we want to be able to handle the interrupt and return to that regularly scheduled programming in the minimal time possible. And if we have interrupts enabled, that's not going to happen. So for interrupt handling, interrupts are typically off. But for anything else, this would be a result of the code that the thread was running, and we're actually okay being interrupted during that. So the next kind of exception we're going to look at is the one we care about, and that is exsys. So interrupts are on, we are still in kernel privilege mode, and we are still using the kernel stack for this thread. So if this is a system call, we're going to call this system call dispatcher. And we're going to pass it the trap frame because, again, the trap frame has all of the information we need in order to figure out which system call we're going to run. Now, I'm not going to show you the rest of main bus interrupt. It handles VM faults and all of those things. We'll talk about that another day. So we're going to go up one directory here, back into Mips, and now we're going to go into the syscall directory. And in the syscall directory, we have the lovely, lovely syscall dispatcher. What's going to happen in here is we have a big old switch statement. And for each different system call code that we're currently implementing and using, we are actually going to have a case. So we've got one for reboot, we've got one for time, one for write, so on and so forth. And again, this code I've already started implementing A2A here, so we have some things filled in. But what's going to happen is we have the switch case, and for each one of the different system calls, you'll see we actually call the appropriate handler. And if there are any arguments to that handler, then we will pass them through from the trap frame. We will take also and you'll also make note of how return values are actually arguments to the system calls so that we can use true returns as being the error code. So this is going to do the body of get PID, the body of wait PID. And then what happens down here at the bottom of the system call dispatcher is we set up the returns. So if there's an error, we put failure in A3 and the error code in V0. And if there is success, we put 0 in A3 and the return value in V0. And then the last thing we do in the system called dispatcher is you'll note that we increment the program counter. Why do we increment the program counter? When you raise an exception, you are disrupting that fetch execute cycle of the CPU. You are preventing the CPU from incrementing the program counter to the next instruction effectively. Which means that if we return without doing this little step here, we'd simply re-execute the system call again and again and again and again, and it's an infinite loop. So in order to move beyond that instruction that caused the exception to be raised, we have to increment the program counter. We're incrementing it by 4 because it's in a number of bytes and each instruction is 4 bytes. All right. So at that point, we return to Mips trap. Mips trap is simply going to return to common exception. And if we go back into low core and back into exception Mips, it's not a directory. Of course, it's not a directory. Let's go to line, I don't know, let's try 250. So what's going to happen is after we return from Mips trap, we've completed execution of the exception handler. We are now going to go down and we are going to restore the trap frame back to the CPU, and you can see us doing here. And then we're going to pop this off the stack. We are going to switch from using the kernel stack back to the user stack, and we are going to return the CPU from privileged mode to unprivileged mode, and then the user program will continue running. So there you go. That is all that happens when you raise a system call, and it's a lot. And when you are writing code, if you are writing your code for performance, you should be very keenly aware of which of your function calls will require or may require a system call. And you should be aiming to minimize those. Okay. So, what this is actually going to look like, we'll show you in a minute. Because I'd actually like to show you some stacks here in a minute. But there's one final thing I want to talk about before we can actually show you what these system calls look like on a stack. So we have the ability, as you know, to run multiple threads. We can do that by having multiple processors, and each processor gets to run a separate thread. We can do that by things like preemption and time sharing and all of those lovely things, cooperative concurrency. Effectively, though, we have the ability to run concurrent threads. We've only talked about that with respect to threading, but the truth is we can actually have multiple processes running at the same time. Because if you really think about it, even though we assign processes states like ready, running, zombie, and so on and so forth, it's not actually the process that runs, it's the threads. So a process would be, quote, running if it had a thread that was running. And a process would be ready if it has threads that are ready. And a process is a zombie if it doesn't have any threads, and so on and so forth. So we have the ability for multiple processes, just like multiple threads, to actually run concurrently. But there's not really much to think about here because, again, it's not the process, it's the threads. So what's going to end up happening here is, and there's many ways that you can actually interpret this code, but when we set up preemption, you'd like to think that your timer interrupt you're setting in the clock is equal to the length of time of your scheduling quantum. But in reality, we don't usually want to talk to the clock every time there's a context switch. So what a lot of systems do is they actually set the countdown of the clock to be a smaller value than the scheduling quantum. So we might set the scheduling quantum to be 15 milliseconds and tell the clock to count down 5 milliseconds. And then what's going to happen, and this is showing you how two processes would work. So you have one thread in process A and one thread in process B. Process B's threads are ready, but they are not running. So process A has a thread that is actually running. So it gets a timer interrupt. We go into the kernel mode to check. We notice that our quantum hasn't expired, so we go back to user mode. 5 more milliseconds elapse. Another timer interrupt. Quantum still hasn't expired, so we go back to user mode. And finally, on the third timer interrupt, that's when our quantum has expired. And so now we're going to do a context switch. And we are going to now let another thread run. And it just so happens that that thread belongs to a different process. And if you actually look at the threads, they actually know who they belong to. So that's kind of neat, right? And then the same thing repeats. So there's not really much to think about here. It's just now instead of all of the threads belonging to the same process, note that the threads that we are doing context switches between may actually belong to different processes. So just keep that in the back of your mind. Now I would like to do this example of showing you what's going to happen on the stack when you have multiple processes and system calls and exceptions. So we have two processes, and process 1 is currently running, and its user program calls fork. So fork is, of course, a system call library function, and then we're going to execute the body of fork, which is to load into register V00, which is the system call code for fork. So just a quick question on Twitch. Why is the timer interrupt shorter than the quantum again? This is just an implementation detail of some operating systems. Instead of having the timer interrupt happen for the length of the scheduling quantum, we'll just set it to 5 and let the clock go about its business, so a smaller value. So the idea here is if you want the timer interrupt to happen at exactly the time that the thread has its scheduling quantum expire, then every time you do a context switch, you would have to communicate with the clock device to tell it to start a new countdown. That could be on your system a costly process. So sometimes instead of having to do constant interaction with the clock device itself, what we would do instead is just have the clock continuously count down 5 milliseconds. And then when that interrupt gets thrown, we'll deal with it. So it really comes down to stylistic details and implementation details and performance of your architecture. But it's just another way it's done. Okay. Anyways, back to this example. So inside of the fork implementation in our system call library, we load our system call code into register V0, and then we raise the exception. The exception getting raised is going to push us into privileged mode. We're going to switch to using our kernel stack now. And now our program counter points at common exception, which has the following address here. So now what we're going to do is in common exception, we're going to save the trap frame to the kernel stack. And then after saving the trap frame, we are going to call Mips trap to actually figure out what kind of exception was just thrown. Now inside of Mips trap, what's going to end up happening is we are going to end up re-enabling our interrupts because they were disabled when the exception was thrown. We're going to re-enable them because we realize this is not an actual interrupt, it's just a system call. So it's safe to have those exceptions and interrupts back on. And then we're going to call syscall to figure out, okay, well, which system call is it? Now, while we are in syscall, we look at register V0 to get the call code and we realize it's fork, and then we're going to try executing sysfork. Now, remember, interrupts are on. Exceptions are on, which means we could actually have a timer interrupt right now. So let's do it. There you go. Timer interrupt. While we were in the kernel doing the system call. Uh-oh. Now what happens? Well, the same thing that would normally happen, except a little bit different because we're already in kernel mode. So what's going to end up happening is common exception is going to run again immediately. And it's going to realize, oh, you're already in privileged mode, so I don't need to change the stack, but I am going to save the trap frame. So you see here we have the trap frame happening again. And then after that, we are going to call Mips trap, and Mips trap is then going to call main bus interrupt, because this is an interrupt this time, because it was a hardware device. Main and interrupts are disabled again. And then main bus interrupt is going to call the interrupt handler for the clock. And that is going to then realize, oh, the scheduling quantum has expired. I'd better do a context switch. And so it's the clock's interrupt handler that is going to call thread yield, which exists only in the kernel. And thread yield will call thread switch, and thread switch will call switch frame. And then we are back here to the switch frame is going to finish saving the context of our thread and load the context of our new thread. So our new thread just so happens to come from another process. And that new thread is then going to start executing its code. So it's going to return from the switch frame, return from thread switch, return from thread yield, return from the interrupt handler from the last time it had been preempted, return from main bus interrupt, return from Mips trap. And then finally we get back to common exception where the trap frame gets restored to the CPU and the thread from process 2 continues running. Fun stuff, right? And of course, as part of that, we're going to be doing things like switching back to the user stack and switching back to unprivileged mode and all of that fun stuff. So remember that exceptions are on when you have system calls, so you can be interrupted. Okay. But let's go back and pretend that that exception had never happened. Let's go back here. So we've got sysfork, and then from sysfork we return and to syscall. Syscall is going to set up our return values. It increments our program counter. Now Mips trap is going to return, and then we return to common exception, which restores the trap frame, and we're going to restore our stack pointer. And then finally, RFE, return from exception, is going to push us back into unprivileged mode, and we're done. That's it. We're back to running our user program. All right. Now, it is 10:50. I'm actually going to leave this here for today. I did want to talk about this one last slide, but we'll talk about it as a review for our next episode. However, next week, as some of you may know or may not know, is reading week. So we will actually have a 1-week break from episodes. You are free to, I don't know, do whatever it is people do on reading week. I didn't have one when I was an undergrad, so I don't know. What do you do on reading week again? Read? All right, anyways, so we will not see you next week. We will see you the week after, and I hope you have an excellent break and Thanksgiving and whatever you decide to do next week.
Introducing Macintosh. It does all the things you'd expect a business computer to do. It does a lot of things you wouldn't expect a business computer to do. And it does some things no other business computer has ever done before. Of course, to do all this, you will have to learn to do this. Macintosh, the computer for the rest of us.
The development of Macintosh by Apple has been paralleled by the work of leading software developers.
It's a great machine. It's a step forward in terms of the way it uses graphics and the speed. And this is a machine that a lot of people are going to be able to afford. That's a very, very useful machine. I was enthused. Microsoft doesn't work with new hardware very often, but we put a team of people on it from the beginning, and we're planning that over half of our retail sales next year will come from Macintosh software.
At the back of Macintosh, you'll find two built-in ports for connecting a printer, a modem, or to Apple Bus, Apple's own local area network, as well as a dedicated port for an external disk drive. The Image Writer printer from Apple is specially designed for Macintosh. By plugging a modem into your Macintosh, you can communicate by telephone with electronic databases and news services. You can also emulate DEC VT100 and IBM 3278 terminals. You can expand the storage capacity of your Macintosh with an external disk drive, just like the one we built in. And if you work with lots of numbers, you'll appreciate the optional numeric keypad. And when you're ready to travel, Macintosh can easily go along. The durable carrying case is strong and waterproof. Your Macintosh, keyboard, mouse, manuals, and software all fit neatly inside. Even fully loaded, the carrying case is light enough to go anywhere you go.
The real genius of Macintosh, the world's newest personal computer, isn't its 32-bit microprocessor or its Lisa technology, or that it captures the power of a mainframe on a board 10 by 10 inches, or even that it costs half as much as computers half as powerful. The real genius of Macintosh is that you don't have to be a genius to use it. Macintosh, the computer for the rest of us.